Hi everyone, and welcome to the October session of the PISC seminars. Today we will have Júlia Barberà from the ICFO in Barcelona. She is presenting us boosting projective methods for quantum process and detector tomography. And would you want, Júlia?
Okay. Well, thank you, Jesus, for inviting me. So as Jesus said, I'm doing my PhD here at the ICFO in the Quantum Information Theory group. And well, this is my first year of the PhD. I had been working on quantum algorithms things, but at the same time, I'm also learning about quantum tomography and certification of quantum devices. And so today I will present the work that I've been doing during these past months at ICFO, along with Leo Zambrano and Donato Farina, who are, Leo Zambrano is a postdoc here in the group, and Donato was a former postdoc. And I will be talking about our methods for projective methods for quantum process and detector tomography. So first of all, to motivate our work, we have to understand the title, and so I will describe every word. So for example, what is a process? What do we mean by a detector in this field? What is quantum process tomography? In an analogous way, what do we mean by quantum detector tomography? And what are these kind of projective methods that are implemented after quantum process and detector tomography? And the boosting part comes from our method where we propose two different algorithms for projecting this out, the output that I will explain that comes out from this quantum process and the detector tomography protocols. And the protocols that we propose, the algorithms that we show more efficient and precise results than current state of the art. So first, let's introduce what a process is. So we know that the states undergo unitary evolutions in quantum mechanics, and we can write them as a unitary matrix multiplying this state, which undergoes this evolution. So I forgot to say it, but please ask any questions as you want, and yeah, feel free to interrupt me during the talk. So as I was saying, we know that states undergo unitary evolutions, and we can generalize this in quantum information when we have a bunch of processes, so a bunch of these processes going on, and we can write it in this way. So this here is the process that we are considering, and using this formalism, we can write it as a sum of Krauss operators, which are these processes acting on the state, on the input state. So one way to represent these processes is via the Choi matrix. So to make it simple, this process can be expressed in this way with the Choi matrix, which is only one matrix encoding this information, and is constructed by considering a system S, and we maximally entangle this system with a copy of it, and then half of this system undergoes through this process. So in this way, we can construct this Choi matrix. And here is important to note that the Choi matrix satisfies two main properties, which are positive semi-definiteness and is also trace preserving. So if we compute the trace over one of the subsystems, it returns the maximally mixed state. So now that we know what a process is, we can, well, one example of a process would be the dephasing channel, for example, where the input state undergoes this evolution, and we have probabilistically a superposition of the state undergoing through this evolution or not undergoing at all. So the state remains the same. So this is what we define here as a process. And we know that in quantum mechanics, we can describe measurements through the POVM formalism. So here, what we mean by a detector is a POVM. And we use these POVMs to measure a state and obtain the outcomes. And we know that these POVMs are, well, a POVM is a set of different matrices that are also positive semi-definite. And the sum of these elements of the POVM sum to the identity. So in the same way as for quantum, and also we know that the probability of observing an outcome n when considering an element of the POVM, for example, in this case Fn, is given by the trace of the input system of the system that we are measuring times the POVM element. So in this way, we can know the probability of measuring this outcome. So one example, as I showed for a process here for detectors, we can consider this POVM, which consists of two different elements, and we are given this state psi, and therefore the probability of measuring, for example, in this case, the outcome plus is given by the trace of the system times the element of the POVM with which we are measuring. So now that we know what the process is and detector is, we can focus on describing quantum process tomography and detector tomography. So what quantum process tomography does is, so the goal here is to reconstruct a process when measuring many independent copies of a state when considering a complete basis set. So one way to describe quantum process tomography is via this diagram. So this is a specific case of quantum process tomography called ancilla-assisted quantum process tomography, but there are two more different kinds of quantum process tomography to do quantum process tomography, but here I will describe this one. So what you do in quantum process tomography is you first consider a state. For example, we consider the Bell state, and what we do here is we prepare first many copies of each state. We then pass them through the process that we want to characterize. So this is the unknown process that in the end we want to reconstruct. So after this, we have the Choi matrix and we want to measure it. So at the end of applying this channel, what we do is we measure with a POVM that is known for quantum process tomography. And in the end, what we can do is we can reconstruct the channel by solving a system of linear equations. Since you have the probabilities after the measurement. So the problem here is that after doing this process, you obtain something that is not physical. So this process is not physical and does not satisfy the necessary properties to be considered physical. And this is due to noise and the coherence effects, and due to the finite nature of measurements. So the same happens here for quantum detector tomography. So quantum detector tomography works in the same way as quantum process tomography, but we skip the part of evolving the state through a channel. And we directly, so here the difference between quantum process tomography and detector tomography, what we want to characterize here is not the process, the channel, but the POVM with which we are measuring our system. So what is unknown here is this POVM, and we want to reconstruct it. So what we do in quantum detector tomography is the same thing as for quantum process tomography, but we directly measure the system. And we can reconstruct in the same way as we did for quantum process tomography, our unknown object, that in this case is the POVM. But here we have the same problem as before, and these elements of the POVM do not satisfy the properties to be a physical POVM. So this is a problem for quantum detector and process tomography. So what is done here is, so we have a problem and we have something that is, so we know that, for example, for quantum process tomography, what we want to reconstruct is a process. And we know that the Choi matrix associated to this process must satisfy the positive semi-definite condition and also the trace preserving condition. But after performing the quantum process tomography protocol, as I said, we obtain something that is not physical. So we can think of this as something that is outside these convex sets that represent the different conditions that must satisfy our Choi matrix. And what we want to do here is to find the closest matrix to the estimate that we found with quantum tomography that satisfies these conditions. So this can be written as this optimization problem. So you have your estimate, that is this J tilde, and you want to find the closest matrix to this one that satisfies the conditions. So in this case, the first condition is the positive semi-definite condition, and the second one, the trace preserving condition. So what state-of-the-art projective methods do is, okay, so we can divide this problem into two sub-problems and relax this optimization problem. So we can first focus on the positive semi-definite constraint, on the projection on the trace preserving set. So we know analytically, and it's, for example, shown in this paper, we know analytically how to project a matrix onto the set of trace preserving matrices. So we can take this estimate and project it to the trace preserving set. And then we can tackle the second constraint, which is the positive semi-definite one. So we also know how to project onto the set of positive semi-definite matrices analytically. So this is essentially done by diagonalizing the matrix, finding the eigenvalues, and setting to 0 those that are negative. So in this way, you can project a matrix onto the set of positive semi-definite matrices. So if you do these two steps, what you find is something that that maybe satisfies some of these constraints, but not both of them. So what you can do to find the closest matrix that satisfies both of them is to iterate between these two. And this is what what is usually done for these projective methods for quantum process tomography. So you can iterate between these two projections, and in the end find something that is in the intersection between the positive semi-definite cone, represented here by this red cone, and the trace-preserving convex set, which is here represented by this blue hyperplane. So in the end of this process, you eventually find something that is in the intersection of these two convex sets, and that is physical. So you find the closest true Choi matrix to the estimate one found via quantum process tomography. So this method is the essence of Dijkstra's projection algorithm, which states that if you have two convex sets and you know the analytical projections onto both sets, by allowing an infinite number of iterations, you eventually converge into the intersection of these two sets. So this seems very nice, but we cannot do infinite number of iterations. So what is usually done here is there's a stopping criteria, and in the end of the process, you obtain something that is very close to the true Choi matrix, but it is not like positive semi-definite, and you have to add a correction. So what state-of-the-art methods do is then mix the estimate that you find after this Dijkstra's projection algorithm. You mix this estimate with the maximally mixed state in order to get rid of the negative eigenvalues. So in the end, you have a matrix that satisfies both conditions, that is positive and satisfies the trace-preserving condition. So this is what is done in the literature. And what we propose is to enhance these methods by substituting this third step by a different one, and to find more precise and efficient solutions. So what we propose here is to, instead of doing this mixing with the identity, is to perform a correction based on the Cholesky decomposition that I will explain now. So any questions up to here? If not, I will continue explaining our method. So I guess I continue. So to summarize, I say that so we propose to iterate between these two analytical projections, and when the Dijkstra's projection algorithm is stopped with given a threshold and a certain precision, we perform this correction. So in what consists this correction? So what we propose is, so we are given this estimate, and what we do first is we project the estimate onto the set of positive semi-definite matrices, into a set of density matrices instead of the positive semi-definite cone. So the difference here is that the matrix will have trace equals to 1, and this can be done using a Smolin's algorithm, which does a similar thing to the analytical projection onto the set of positive matrices. But here we have to make sure that the trace in the end is 1. So we essentially do the same thing as before. We cut the negative eigenvalues while preserving the trace. So after this algorithm, after applying this algorithm to the estimate of a Choi matrix, what we find is a a matrix that is positive, and we know that this matrix, when we have a positive matrix, we know that this one can be decomposed via the Cholesky decomposition in this way. So a positive matrix can be expressed by this multiplication of lower triangular matrices. And once we have this decomposition, we can tackle the second constraint, which is the trace preserving one. So the problem that we have to solve now is this one. So we can get rid of the positivity constraint, as we know that for sure the matrix E will be positive. So the problem that we want to solve now is this optimization problem. So we want to find the closest matrix to the positive one that satisfies the trace preserving condition. So this for sure will give an upper bound to the exact solution. So remember that J star is the exact Choi matrix, which is the closest one to the estimate that satisfies both conditions. So for sure, the solution to this optimization problem will give an upper bound to the exact solution. So this optimization problem can be solved using Lagrange multipliers. So what we want to, so Lagrange multipliers work in the following way. So you know that the cost function that is the thing that you want to minimize is the distance between this positive matrix and the one that you want to find. And the constraint is given by this, so by the trace of the matrix, which equals to the maximally mixed state. So from this, we can build our Lagrangian, which is the cost function minus our constraints, that in this case, we only have one. And if we derive this equation and find the minimum, we can solve the problem analytically. So what we find here is that the solution to this optimization problem is given by this equation. So this E dagger is the input to this optimization problem. That is the positive, so the density matrix obtained after running 0.1. So if we perform this transformation, what we obtain in the end, this Y stars correspond to the solution of the problem, which is an upper bound to the closest Choi matrix that satisfies the positivity condition and the trace preserving condition. So to summarize what we are proposing, I show you the pseudocode of the algorithm. So in this way, maybe it's more clear what we are doing. So what we do is we first give as input an estimate to the Choi matrix. So we generate a Choi matrix from a hard random matrix, and then we add noise to this matrix, generating our estimate of a Choi matrix that does not satisfy the conditions. So in this way, we can simulate the quantum process tomography that is done in experiments, which returns a matrix that is not positive semi-definite and does not satisfy the trace preserving condition. So once we have this input, we run the Dijkstra's projection algorithm, which is this subroutine, and that iterates between two different projections. So we first project onto the set of trace preserving matrices and then to the set of density matrices. So by alternating between these two projections, eventually we get closer to the true Choi matrix. But as I said, in the end, we don't obtain something that is physical. So we perform the correction that we propose, which is based on the Cholesky decomposition. So after many iterations of Dijkstra's algorithm, we perform this CVA correction, which is what we call the Cholesky-based approximation, which is essentially multiplying the output of the Dijkstra subroutine by two different unitaries. By a unitary. And in the end, we find something that is physical and that satisfies the two constraints. So this is a summary of how this algorithm works, and we implemented it in order to evaluate the performance of our algorithm compared to the state-of-the-art methods. So what we did is we generated 100 different random input matrices, and we run our protocol, which is this CVA1, CVA. So this CVA, which is depicted by the black line in the plot, corresponds to our algorithm when allowing only one iteration of the subroutine. And what we show in this plot is the distance between the exact Choi matrix found via semi-definite programming, which is what is usually used for solving these optimization problems, but is very expensive and it's not scalable. So that's why these projective methods are considered. So we compare here the exact solution found via SDP that can be computed for low-dimensional systems, and the matrix found using our protocol and different other algorithms that are currently used as projective methods. So as I was saying, what we show in this plot is our algorithm with only one iteration, which is the black line, which can be benchmarked with the TSS, which is a different algorithm that considers the projection instead of the density matrices set onto the set of positive matrices, and then they project onto the trace preserving set. So if we compare both algorithms, we see that the performance of ours is better in terms of precision, since we are getting a solution that is closer to the exact solution. And for the iterative algorithms, which are this HIP1 and the Dijkstra plus CVA, which is our proposal, we can see that in our case, we obtain a 3 order of magnitude improvement in precision against this HIP. So what they do in this algorithm is they switch between this Dijkstra subroutine, where they project between the trace preserving set and the set of density matrices. And when a condition is satisfied, they switch to a different mode, which is this hyperplane. Well, they call it this hyperplane method, where they consider only half spaces instead of the whole space in order to obtain a more efficient computation. So when comparing our method and theirs, we can see that we obtain more precise results. And in terms of running time, what we see is that we obtain more precise results without compromising the computational efficiency, as the iterative methods run in the same time, and the two steps algorithms also run in more or less the same time. So this was everything for quantum process tomography, but this can be extrapolated to, so the analogous thing can be done for quantum detector tomography. And we also simulated this for quantum, so we implemented these projective methods for quantum detector tomography. But there wasn't a lot of work done in this direction, so we could only benchmark with one algorithm, which is this one called TSE, which is a two-step algorithm that only performs two projections. So we can compare this algorithm with ours with only one iteration, which is essentially considering the projection onto the set of positive matrices, and then projecting, performing the correction that I have explained and that we propose for our method. And when comparing both results, we see that we get the same precision. But when we apply the Dijkstra subroutine to both methods, we can see a 2 order of magnitude enhancement in precision. So this was very nice, since the only method used right now for projecting the output of quantum detector tomography was this TSE, and only considered this two-step projection. So by introducing this Dijkstra subroutine, we can obtain more precise results. And in the same way as for quantum process tomography, we do not compromise the computational efficiency, as we can see in this plot, where we show the running time as a function of the dimension of the problem. And we can see that the iterative methods only run an order of magnitude greater than the two-step projections. So, and also here in this plot, we show the yellow line, which is the running time taken by to finding the exact solution via semi-definite programming. That, as I said, is what can be considered to solving these optimization problems, but it's very expensive to use this method. So that's why that's why people consider using these projective methods in order to obtain more efficiency in computing the true Choi matrix to the estimate one given by the process and detector tomography. So, well, it was very short, but from this work, we have been able to develop two different methods for quantum process and detector tomography that run in the same time as current state-of-the-art methods, but we obtain more precise solutions. So we had been able to extend the quantum process tomography method to also POVM tomography. So, well, thank you so much for your attention, and feel free to ask any questions.
Thank you very much, Julia, for such an interesting talk. So now it's time for the questions. If anyone has any...
Yeah, and please feel free to ask any kind of question. Yeah, I know maybe it was a bit technical, but yeah.
Any question? Okay, I don't see for the moment anyone, but yes. Okay. Is someone talking, or is it your audio, Julia? No, I think it's in your audio. Okay. In Welsh, or to see if someone starts with some question, I will start. Okay, I wanted to ask you, Julia. Okay, you have proposed or studied two methods for this for quantum process and detector tomography. which are you currently working in another methods, or are you developing this work for more than 6 qubits, or this is too computationally, this has a very high computational cost, or which are your concerns
Yeah.
right now?
Well, actually, these methods can be currently used for well, as a projective methods after performing this quantum process and detector tomography. And the thing is that, yeah, one question that we were asked by the referees is that if these methods are scalable and if you can, so how do we expect to behave with the dimension of the system if we increase the number of qubits? So the thing is that with these methods, we don't solve the exponential issue of semi-definite programming methods. That is what is used, as I said, for solving these optimization problems. But we can somehow speed up the methods and get approximate solutions. So regarding the scaling, we've been trying to simulate it for higher dimensional systems. And with the resources that we have right now, we have simulated for systems of 10 and 12 qubits for quantum process tomography. And we have found that actually our method is more precise than current state of the art. So yeah, and requiring the same computational time.
That's nice, interesting. Thank you. Let's say that anyone has another question. Wait a bit, if someone.
There's a question in the chat.
There is a question in the chat. I
Wait,
didn't see it, sorry. Okay. Yeah. Okay, a question from Sebastian. Okay, I will read it.
Okay.
No problem. Okay. He said that he's not, okay, so very interesting talk and everything. So he says that he's not really an expert on the field. So maybe his question is rather naive, but this would help to characterize the common errors that appear in quantum devices such as the IBM chips.
So you mean characterize these chips in terms that? So what did you said that to characterize what?
The common error that appears in quantum devices such as the IBM chips. If this could help to characterize. Maybe Sebas could do a clarification. Yes, to characterize the non-unitary dynamics that appear in real devices.
So actually, kind of yes. So what happens here is that after quantum process tomography, you get this non-physical estimate of the Choi matrix because you have noise and decoherence. So using these methods, you correct these negative eigenvalues that appear when you have noise in your devices. So somehow you could you could characterize this error by running. So the thing is that you could characterize the error after running quantum process tomography and doing more Monte Carlo. So in the end, you get the error that these circuits produce in your output that is not a physical estimate. So yeah, I guess it could be done.
Okay, so it says thank you very much, Julia.
Okay.
So let's see if someone has any other question. If not, we will finish the session, but let's wait a moment. Okay, there was a final question. I think he's writing with the debate. Okay, he says, does this method also apply to systems that instead of qubits are composed by qubits, systems with d+2 levels?
So it hasn't been done, but I guess it could be done, and we could try it.
Okay,
But
he's
I-
basically commenting.
sorry.
Sorry. Yeah, he's basically commenting that, or if the mathematical structure is restricted to the Pauli matrices. Sorry for interrupting.
So I was explaining, but I don't know if you heard me.
I think the connection was cut and we didn't hear.
Okay, so I was saying that maybe due to the formalism that you're using with the Choi matrix, I'm not completely sure that you could extend it to qubits. But as I said, as I was saying, I have been working on this for a few months, so I'm not an expert at all in this topic. So yeah, it could be further investigated, but yeah.
Okay. It's interesting, yeah. So thank you very much, Julia, for your very nice presentation and for answering all the questions. So yeah, I think we can finish this October session of the PISC seminars. Let's thank again Julia for the presentation. Yeah, I think we can finish it. See you the next month with the next edition of the PISC seminars, and yeah, see you soon.